Good evening and welcome everybody to Nsimplex Pachinko. This is Obi-Wan Pez. And we are having another math night. Woo! Hey Benji, how you doing? Got dust everywhere because I haven't actually done this properly for 2 weeks. I also haven't plugged in the tablet. Man. You know, I was even a couple of minutes late because I was like thinking about getting stuff ready. Yeah. Didn't do the one thing I actually kind of needed. Alright. So, how's things? Things have been kind of crazy over here. Let's see if I can remember where anything is. Format background, blue graph. Okay, there we go. Mine's pretty good. We had, stuff for the kids, and went to our our institution service, so it's pretty good. Today is 2022-04-20, and well, we have yet to name this because, quite frankly, no. I know what the error is. I probably ended it in the dash. There we go. Alrighty. Absolutely. Let me know what you saw. I also want to, because we did this in pre-calc class today. No? Interesting. This thing was correcting me earlier and making my circles perfect. Now it's not doing that. That's frustrating. Enhance inked shapes. There we go. Perfect. Yeah, we could do religious iconography. That'd be interesting, but I don't have enough of a background in that particular section of geometric history, nor religions. Anyway. We were today in Trig doing our section on the sum and difference formula. So I thought I'd just, while we're hanging out and waiting for Benji Boy to type out their question, we're going to work a little bit on this one and then eventually finish it. All right. So given two angles that are anywhere in any circle, so it does not have to be a unit circle, it does not have to be anything else. Yes, I'm making it slightly more challenging for myself, but oh well, it's fine. Given that the farther along angle, alpha is going to be greater than beta, r is any positive real number. I know even Megalomorph would not necessarily like the angle, or sorry, the radius of the circle to be either 0 or negative. I know it works fine in polar coordinates, but still. Assuming r to be some sort of constant. We're going to say that each of these points here, due to their location on the unit or on the circle, super easy. Okay, so total of the surface area, yep, equals the perimeter Okay, so the surface area base chi, so we're getting a rectangular based prism, or in this case, I guess you're saying it's a square. So that all these should be the same size. And then we've got a stick of butter. Yep. So if you're looking at the individual surface area, so how much of this would you need to paint if you were trying to put paint on the entire outside of this thing? Okay. So the lateral area, just as Megalomorph said there, is going to be the perimeter of your base multiplied by the height. Height of your prism. Yeah. And I'm a big advocate for that too. You do need to find the surface area of the bases. So if you're talking about a solid prism that is like, say, a deck of cards like this, you know, the box with a deck of cards in it, then you're looking at needing to take the surface area of both surfaces, and then when you take the perimeter and multiply it by your height, that gets the entire lateral area. So one of the ways that we can prove that is to say, okay, what's actually happening here? And it doesn't, like Megalomorph said, it doesn't have to be a square. It could be any shape you want, as long as it is a prism. So that shape is then being projected into the third dimension a straight distance. It's not curved. It's not going to be like, you know, out and back or anything like that. It could, yeah, if it's slanted, it causes all sorts of other problems. But again, the same reasoning, yeah, the same reasoning goes here. You don't want to think of this in terms of, oh, what's the formula for this thing? No, no, no. As Megalomorph said, think about it as individually, what is it that we're doing just in general? So anytime we're doing any sort of what's the surface area of this thing, we want to know what is the area of every single side. So the volume of a slanted prism is the same as the volume of a straight up and down prism. The volume. But the surface area is going to be extended because the more you slant it out, the longer the height of that particular shape is going to get. So if you make one out of a board that just goes like straight up and down 6 inches, it's not super long. But if you make one out of a board that's 6 feet long and slants out to get to the same height level, then you got a bit of a difference. Right? Your volume will be the same. And that seems really weird and wrong, but it is actually true. But your, exaggerated version will have a different surface area. You're going to need a lot more paint the more you slant it. So yeah, we can prove all sorts of stuff doing that. If we say we get our height here, we get our base sides can be, let's just do X and Y, right? Oh, sorry. 6 inches, 15 centimeters, give or take. It's a foot, like. Oh man, we live in a psychotic country. Okay. Even the people who once, like, invented the imperial system have now moved on. Let's not get started. Yeah, so, what was that? That's 1524. Yeah. Okay, anyway. So if you have your 3 dimensions, X, Y, and H, H being the height of this prism, and X and Y being the lengths of a rectangular base, then here the perimeter of your base is going to be 2x and 2y. Times h. And again, this gets you the lateral area of, like, the tube part. So how much box would you need to ship an item? That kind of thing. All right, and the reason that works is that you can unroll this thing. And if you had this thing unrolled, we would find that h here would be the height there. What was what? I don't see anything. What happened? Like, I don't even see anything. So I don't know. Oh dear. That's interesting. Man, I usually it pops up and it says something. But oh man. I guess it's a little overzealous. So anyway, yeah. So what would happen here is if you unrolled this box, if you slice it down one of the sides and then unfold it, you would get two parts which had width y, which are opposite each other. And then we'd have two that are opposite each other here, which would be distance x. So this one got cut too short here. So let's erase that. Extend this a little further, like that. So you can see here that if we unroll this thing, the lateral area is now a rectangle. And that would be true for all prisms. All prisms. So it doesn't matter what shape you have. What is going to change is then what these are all labeled. So these are all going to be x's and y's. That's it. If you have something that's like an irregular hexagonal prism like this, right, and then you unrolled, this thing would end up looking like this, and we have like 1, 2, 3, 4, 5, 6, like that. So you get side 1, side 2, side 3, side 4, side 5, and side 6. And then again, the height of the prism is your height of the rectangle. Yep. Just pretend it's a box that got shipped in the mail. And you can slice it open. So here the lateral area is going to again be just the sum of all the sides, so the perimeter times the height. So again, lateral area. Sum up for the length of make that the width. Not like it matters, but so if you sum up all the sides, you get the width of the lateral area, and then the length of the lateral area is your height. So again, rectangular base makes it nice and easy. These are repeated values. So x plus x, y plus y. 2x, 2y. And then multiply by your h. Yep. And then here, you'd have to say, okay, to get the base area, this is where you get, and again, now it depends on what shape you're talking about. So find the area of your bases, and you say, well, there's two of them. How do you mean? Sorry. All right, and then to get the total surface area, you're going to add these two things up. My students were complimenting me at the beginning of the semester because of my beautiful handwriting, and I'm like, it's like most of the time it's affected by whatever software I'm using. It cleans it up just a little bit, just to make it a little bit nicer. Um, then complementing, yes. Well, this is also years upon years of practice in front of, you know, having to write for other people. So Megalomorph, were you counting on the fact that I would not notice the I to E difference? There was something else I was going to mention about this, but I don't know. I guess like the cone. There we go. So for a cone, the lateral area becomes a bit different because now you're oh wait. Yeah. Okay. I didn't actually want the cone. I wanted a cylinder. So that's fine. I know shapes. It's Whoa. Nope. Nope, nope, nope. Okay, seriously. Uh, that's fine. God, that looks awful. All right. There we go. All right, so you get something that looks like this. Right, cylinder-wise. So for this one, you end up getting something very similar. Yeah, that's why I said, oh wait, no, I didn't want to do a cone, at least not yet. So here, we can treat our cylinder the same way we do a regular prism. This is just a circular prism. Yep. Pi d or 2 pi r gets you your perimeter base, and then you multiply by the height, and that gets you to allows you to unroll it again. So now you're unrolling the cylinder, and the outside of the cylinder just becomes a rectangle. And it's just like all the rest of these, but now it's 2 pi r across instead of like discrete amounts that are being added up. Then times your height, so that gets you the lateral area. And then your bases are going to be twice r pi r squared. Yep. It's one of my favorites. Oh no. Man, that would be... Oh, now you got me off on a tangent. Tangent. Oh, slanted. So if you were to make a cylinder whose sides almost nope, that was interesting. Nope, that's not what I want either. There we go. So if you make one like this, and you say that this is going to be your cylinder, but now it's tilted to the side. Yep, just like the prism that we talked about. If you... That was weird. Yeah. So, right, like a slide on a playground or something like that, you could take the... Right, so if we did this... That's not exactly perfect because I did it wrong, but whatever, it's fine. So yeah, if you create something like this, the volume again is going to be the same as just the straight up and down prism because the height is the same here. Whenever you draw heights, you always draw straight down compared to our base or wherever. So our height here, h, is going to be the same as just a regular square prism going straight up and down. And then the area's base is going to be the same because it's the same square. You just moved it over a bit. So yeah, volumes are equal here to straight up and down, but very different surface areas. And in this case, you're looking at parallelograms in the side shapes. You're going to still be looking at rectangles along the front and back. Right, I mean, that's what I did here. It's just dot, dot, dot out. Yeah. So, man, I have one of those. What does it do? So if it's on its side like this, it's going to roll straight back. Okay. So the... Alright. What would you like to talk about? What kind of exercise would you like? Algebra is a very wide topic. Oof. So if I'm contending that so like what subject? Well, I mean algebra, sure, but like do you want something with areas or do you want something with All right, so All right, try this. So the surface area for a cylinder with radius 10 centimeters is 800 square centimeters. So what is its height? And I guess we'll make that, let's make that 800 pi, just to make it slightly nicer. 800 pi centimeters, square centimeters. That might take you a minute. All right, why? So that would be true if I had said find the lateral surface area is given as 800 pi square centimeters. So you got the right idea. But that's only the lateral area. So you have to include the base areas in all of this as well. Yep. Nah. No worries. I still do stuff like that all the time, so don't feel bad. I have most likely done it on this channel several times. All right, so let's come back to this for a little bit here. Nope. You got the right idea. Now you've got the pieces. Right, so alpha is going to be further along than beta in terms of this. And it doesn't actually matter where we put this. It could be both in quadrant 1, 1 in quadrant 1, 1 in quadrant 2, or 4, or anything. Doesn't matter. It's all going to be the same thing, just a slightly different picture. Alright, so the location of the point we're talking about here is going to be r times the cosine of, well, I guess I don't need parentheses really all that much. Angle alpha is out here, so cosine of r cosine of alpha, comma, r sine at alpha. And then this point out here is going to be, similarly, r cosine beta by r sine beta. All right. Now that's all well and good, but it doesn't really tell us anything necessarily about this particular. See if we can't copy paste this nicely. Good. Yeah. Okay. So we copy paste this circle here. This is going to get us an identical twin to what we had there. Nice. I'm liking that. I just kind of, so I drag out a line and then I just kind of shake it a little bit and then it snapped right to where I'm sitting. Now I could actually, does it just work if I, yeah, okay, I didn't have to actually shake it. It's just. Alright, so anyway, we got this stuff. Now, if we take our original alpha and beta angles and then swing them back around the original, the original circle to put them in standard position, this means that our beta, the short angle, is going to be back in standard position along our x-axis here. That means that its position is now r comma 0. It is always difficult when you don't have a piece of paper. All right, and this is somewhere like here-ish. So now we have this angle here. The angle between them is still, again, alpha minus beta. Yes, I saw that. I was like, wow. You had to actually issue a statement, huh? So, alpha minus beta is the new angle in standard position that is between these two angles here, which means that this new location up here is going to be r cosine of alpha minus beta, comma, r sine alpha minus beta. It doesn't actually matter which angle is in there. It's always just whatever angle is in standard position at that particular point. Ta-da! There we go. So, yes, Benji boy, 30 pi centimeters. So, awesome. Good job. Wait, hang on. Nope, nope, nope. You don't need the pi. Alright, so coming back. What we're saying is that the two summed up is going to get us our 800 pi centimeters. So that's 2 pi RH plus 2 pi r squared. R was 10, so 2 pi times 10 times h plus 2 pi 10 squared. Which then gets us here 20 pi h plus 200 pi. So here, subtract off the 200 pi. So 20 pi h is equal to 600 pi. And then divide both the 20 and also the pi. So that was the part that you left out. But again, you said you are not using a piece of paper at the moment, so it's quite understandable trying to do things in your head. All right, so here we got 60 over 2 is just going to be 30. And then that's equal to 20 is out and pi is out, h. So yep, h is 30 centimeters. Awesome job there. All right, so then with this angle now, we've got two different angles which get us the same like shape, overall shape. If we want to, for instance, we can draw in the line that, wow. Nope. Can draw in the line that goes from here to there in both of these pictures. Now, had I drawn this properly and actually had the actual correct angles plugged in, then this would look a bit more similar. But this angle is far too small compared to that one. Oh well. Okay, so over here, if we label this distance here D, and this distance here D, we can see that these are going to be the exact same thing. Well, you kind of need to understand trigonometry a bit. So the sine function, S-I-N-E, is going to output the height of the point on a unit circle centered at 0, 0. So because we have these points at 0, 0 that are the centers of the circle, we want to know what the height is of this point as it moves around the circle. So the height of that is given by the sine function, which, as the Megalomorph said, the sine function is usually written sin, which is sin. So something that you have, a morally criminal act against God himself. Amogus, how's it going? Good evening and welcome back. So yes, the sin of eating pie is equal to 0, therefore it's not a sin. All right, in the case of what we have here, in both cases, what we're going to do is create a right triangle based on the distance that we have written in green, and then the dotted lines, which are going to get us the horizontal and vertical components of that distance. The distance is given by the 2 points that are on either end of that line. And what we want here is the distance in the y direction, which often is written as y2 minus y1, and the distance in the x direction, which is often written as x2 minus x1. So here, we now have a right triangle, so we can create Pythagorean theorem based on that. So d squared is going to be equal to parentheses x2 minus x1 squared plus parentheses y2 minus y1 squared. So, again, this is one of those things where the book that I'm working out of says, like, oh, you get the distance by doing the square root of this thing, and you're doing a Pythagorean theorem. So, like, do you really need to take the square root of all this? If you're just trying to find the distance, sure, but you can do that later. You don't need to memorize a formula. You already know the formula. It's the Pythagorean theorem. So don't memorize another one. So I was telling a bunch of my students today, you know, don't memorize the formula. You already know what the Pythagorean theorem is. There you go. You don't need to worry about the whole x2 minus x1 thing. You're trying to find what's the distance in this direction and what's the distance in this direction. You know how to do it. I've been telling you how to do it all semester long. So in both cases, this one here and this one here, we have the distance formula, which can be given by two different sets of points. And that gives us a lot more information to work with. Not to mention, the one down at the bottom on the right is getting us in terms of the sine and cosine of alpha and beta alone. And the one over here is getting us stuff in terms of the sine and cosine of alpha minus beta. So there's a relationship that needs to fit in there. Yeah. And pictures are way easier to remember. Yeah. Exactly. It's one of the reasons that I, as much as I can, try to tell my students about the history that goes behind the math. Even if some of it is somewhat apocryphal, it's easier to remember just because, oh, yeah, I remember that story about that guy who was like, why are you wasting your time with such imaginary numbers? All right, so the one on the left is going to be d squared is equal to, and then here, x2 minus x1, again, it doesn't matter which one we pick, but r cosine of alpha minus beta minus r parentheses squared plus parentheses y2 minus y1 is r sine of alpha minus beta. Oops. I mean, that is where it ends, but I should go one more step here. Minus 0 parentheses squared. So subtract your x's to get the component in the horizontal direction. Subtract your y's to get the component in the vertical direction. And then do the same with the other triangle over here. So our d squared there is going to be equal to parentheses x1 r cosine alpha minus x2 r cosine beta parentheses squared plus, do your y's just the same, r sine alpha time, nope, not times, minus r, oops, man, sine beta parentheses squared. All right, and from Russia with Math. Good evening and welcome. Thank you for the follow. Welcome to N Simplex Pachinko. My name is Obi-Wan Pez, and this is my math streaming channel. Oh, and I also need to give a shout out and thank you to one of my close friends in real life, More Circle, who helped out and subscribed via Prime. So thank you very much, More. More's more. Anyway. Yeah, he was basically waiting with bated breath until I said, "Oh, I got affiliate," before he subscribed with Prime. And if anybody else wants to toss some Bezos bucks in there, I'm very happy to take those. I like I said before, I don't particularly need or want anybody to like subscribe with their actual money. Um, like it's wonderful if you do, and I thank you from the bottom of my heart. But it's not necessary. If you would like to give your money to a streamer who like actually works at streaming for a living, it would be a better use of your money. You know, no offense. Or if you have any particular charities that you're looking at recently, especially with the recent conflicts in Ukraine, helping out to try and help the like helping out the civilians who are being thrown out of their homes at the moment, that would be lovely if you could help them. Anyway, so if we're looking at this, Brady Heron did a video recently with he does number file on YouTube. On number file 2, he just recently posted an interview with Val Narushin, who's in Ukraine and is a co-author of a paper to find the universal equation for the shape of an egg because he is a poultry scientist. So, it's a very interesting 14-minute video on number file 2. I highly recommend it. It's a good watch. And the guy is very very humble. He's a very good watch. Yeah. Egg. Okay. So, one of the points that I brought up earlier was that these two distances are the same thing because we're creating two different triangles here, but really they're actually the same triangle. So we have this angle here, which is between our two sides, the initial and the terminal, which has a measure of alpha minus beta. Then we also have the two sides, which go from the center out to the edges. Those are the radii of the circle. So therefore we have a side, angle, side congruence between these two triangles. Okay, so these two distances are identical to each other. Therefore, we can set their individual equations equal to each other. So here, this is going to be, let's go over here, r cosine alpha minus beta minus r squared plus parentheses. And now at this point, I'm just going to square the first part. We're not going to worry about the minus 0 because something minus 0 is just itself. So we have the identity here with r sine of alpha minus beta, just that. So r sine parentheses alpha minus beta, that is being squared. And then that's equal to this whole right-hand side here. So r cosine alpha minus r cosine beta, parentheses squared, plus parentheses r sine alpha minus r sine beta, because nobody ever proves it except me because I'm psychotic. And if you're following along or zipping ahead of me, you're going to see some really interesting stuff in about 2 minutes. All right, this is going to be multiplied all out. So this is going to be r squared cosine squared of alpha minus beta minus 2, and this is the whole Pascal's triangle thing, where we're doing a plus b parentheses squared. So we get a squared plus 2ab plus b squared. So here, this is the 2ab part. Yeah, and it's much, much simpler. It does involve several properties, but the good thing is that by the time you're learning this, you've already learned the trig properties in like the previous 2 sections. So you're using something that you just had. All right, so this is going to be 2 times r squared cosine of alpha minus beta. And then here, plus r squared. Easy enough. Okay, plus this is just going to be r squared sine squared alpha minus beta. And that's equal to. Now we're just going to bump onto the next line because, quite frankly, I don't have the room for this. This is going to be r squared cosine squared alpha minus 2r squared cosine alpha cosine beta plus r squared cosine squared beta plus r squared sine squared alpha minus 2r squared sine alpha sine beta plus r squared sine squared beta. And now we could say here, all right, look, we've got r squared in every single term. So if we multiply by 1 over r squared, it eliminates all those terms, which means that this is radius invariant. Which is not really surprising if you've ever seen trig of any kind, because all the trigonometry is it's looking at taking the ratios of these side lengths of triangles. So it's going to be like the cosine is the width divided by the radius. So if you're dividing by the radius, it's going to normalize it back down to a unit circle. So radius 1. All right, so all these terms no longer have an r squared, and we can arrange these in such a way that they become a little nicer. So for instance, we've got a cosine squared of alpha minus beta plus a sine squared of alpha minus beta minus 2 cosine of alpha minus beta. That's equal to, on the other side, again, all of our r squareds are gone. We have a cosine squared of alpha plus a sine squared of alpha here. We have a cosine squared of beta over here, and we have a sine squared of beta over here. And then here we have what's left is going to be our minus 2, the r squared's gone again, cosine alpha cosine beta, minus 2, sine. Sine alpha sine beta. So now these right here, cosine squared alpha minus beta plus sine squared alpha minus beta, and also cosine squared alpha plus sine squared alpha, and also cosine squared beta plus sine squared beta are all 1. Oh, shoot, I missed a term. Right, and this one. The plus r squared here, when we divide by r squared, it's a plus 1. That goes in here. Let's just take that to the beginning over here. So plus 1. You can totally see that. It's fine. Okay, so on the left, we have 2 minus 2 cosine of alpha minus beta. On the right, we've got a 1 plus a 1, so 2. minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. So subtract 2 from both sides. And also we can divide everything, left and right, by negative 2. Divide. So here when we subtract, it just goes away and becomes 0. So that's gone. Then we divide by negative 2 everywhere. We get the cosine of, that's behind my head. We'll get there eventually. Oh, you're going to like this one. I did the same thing. Originally, when I had done this, I was like, okay, so one, we could use the Pythagorean theorem, but that's going to be disgusting because you have to square something that's got multiple terms with sines and cosines in both places, and it'd just be huge. Like, I don't want to do that. I do not want to do that. So then I was like, okay, we're not doing that. Then I said, okay, what if we rearrange this and put our initial side on the y-axis and then went out into quadrant 2. And when I tried to, quadrant 2. When I tried to do that, it came back to the exact same formula for the cosine function. I was like, okay, that didn't work. And I just look at my students, I'm like, I'm really sorry. That was not nice. They're like, oh, fine. So then, I can't remember, I think it was this last year, I figured out how to do it because it was like, oh, well, that's stupid. Of course I could do it that way. You're going to like it. I'm going to save it here. See if you can get it in the next 5 minutes. Okay, so then here we've got the cosine of alpha, cosine of beta, minus, plus, right? Divide by negative 2, we get a plus in between. Sine alpha, sine beta. So this is called the cosine sum and difference formula. Now, some of my students very aptly noted that I had only done the difference here. So like, how do you do a sum? Well, if you let beta be, instead of beta, you let cosine of alpha minus negative beta, you could maybe. I'm not sure about that. Yes. If you frame it correctly, yes. All right, so then here, if we change beta to negative beta, this allows us to have cosine of alpha times the cosine of negative beta plus the sine of alpha times the sine of negative beta. And this becomes very interesting because here, cosine, if you look at it in terms of if you look at cosine in terms of its positions, so whenever we have a positive theta, it looks something like this, and we get a point where it's located called xy. Then negative theta is going to be going in the opposite direction, negative theta, and the point that it occupies is in exactly the same x location, but its y location is opposite. And that's true no matter where you are in the circle. So if you're in quadrant, this way. If you're in quadrant 3, both your x's and y's are negative. And then if you do a negative theta, that goes instead down and goes to quadrant 2. So your y value is now positive, which is opposite what you got originally for theta. So negative, your negative value gets you a positive value. And again, your x value is the same. So negative theta goes down, and our x values are identical, which means that the cosine values are identical for cosine of negative beta and just cosine of beta. Because cosine is an even function. You could also go that way. And then the cosine of alpha just stays the same, nothing changed there, plus sine of alpha times sine of negative beta is going to get you y values, and those are now negative compared to the original. So sine is an odd function, so we're going to get a negative sine of beta as a multiplier. And then we just kick that out to the front, and it becomes cosine of alpha times the cosine of beta minus sine alpha sine beta. So this is the cosine of alpha plus beta. Some of the ways that I help my students remember what this is, it doesn't always work, but you say when you have a cosine, first of all, no matter what function you're looking at, just what you see here as the first part is always going to be the first thing that you see on the inside of this particular function. There you go. Yep. That's the one. Right, so the cosine of alpha is reflected right here as the first thing. And also in terms of cosine, your functions will be the same so your cosine matches with your cosine, your sine matches with your sine, but at a cost that our signs between the numbers have to be opposite each other. Now, I'm not saying it's a good mnemonic, but it can help some of the students understand how this all works. And the other thing that you need for all of these formulas is that all four possible combinations of sine and cosine and alpha and beta are present. So all of them. Cosine alpha, cosine beta, sine alpha, sine beta. All four need to be present somewhere. So, let's see. Usually the way that I go with this is that I will also write this out as just the sum and difference formula, all one thing. Yeah, it doesn't like math terms. Text to speech, ugh. So our cosine plus of alpha plus or minus beta is going to be equal to the cosine of alpha times the cosine of beta. And again, we get the plus and minus in between. However, it has to match. So the top one is alpha plus beta, which matches with the cosines minus the sines. And cosine of alpha minus beta matches with the cosines plus the sines. So here's your sum and difference formula for cosine. Really. Whatever. That's fine. Right, and then just like you said, Megamorph, if we want the cosine of, well, okay, we want, the ultimate goal is to get the sine of alpha, let's do minus beta just because. Right, we want the sine of alpha minus beta. So this is the same as the cosine of pi over 2 minus parentheses alpha minus beta. So using the cofunction identity, we can say, these things are equal. And then here's the trick, right? You shift which ones, or you do the association as far as what you're actually subtracting. So this is the same as the cosine of pi over 2 minus alpha plus beta. And then we want the cosine sum formula. So that's going to be equal to the cosine of pi over 2 minus alpha times the cosine of beta. Between them is addition, so between the functions is going to be subtraction, times or minus the sine of pi over 2 minus alpha times the sine of beta. And again, we use the cofunction identity to say that the cosine of pi over 2 minus alpha is just the sine of alpha times the cosine of beta minus sine of pi over 2 minus alpha is the cosine of alpha times the sine of beta. So that's the sine of alpha minus beta. And then, if you notice, we didn't actually change anything about the other two functions, right? The cosine of beta and the sine of beta are in exactly the same position. So if we want to switch the sign that goes between and make it alpha plus beta, then that's just going to, again, switch the sign that's between the functions, because the sine of beta is the one that switches. So that's going to be a plus here for the other one. So now our two functions are opposite each other that are being multiplied together. We got a sine times a cosine and a cosine times a sine. Again, all four of them need to be present, and the one we start with is our sine of alpha, which is written there. And again, since the functions are opposite each other in the product pairs, then the sign between them is going to be the same. So one thing is the same, one thing is different. Again, not a great mnemonic, but it helps some of my students, so I go with it. And I will always say, if this mnemonic does not help you, don't remember it. You're just going to confuse yourself. So practice it, and just keep practicing it. Yeah, that's one of my favorites of just like things to do in terms of trig identities. Some of my students just looked at that and were like, what? And then this is super easy because from here you say, okay, what if alpha is equal to beta? Right? So you do the sum and difference formulas. Well, if you do the difference formulas, you get alpha minus alpha. So it's just 0. So cosine of 0 and the sine of 0, which is a very helpful way to double check that you got your formula right. Because again, cosine of alpha minus beta is going to be equal to the cosine of alpha minus alpha. So now we've got the cosine of alpha times the cosine of alpha. Minus here is plus down here. Sine alpha. Oh, look at that. It's the cosine squared of alpha plus the sine squared of alpha, which we better hope is 1. Right? But then up here we say that cosine of alpha minus alpha is the same as the cosine of 0. So the cosine of 0 is equal to 1 is true. Right? Those are equal to each other. So we're good there. That's why it's not a proof of the Pythagorean identity. It's a double check that you got your formula right. And then the sine of alpha minus beta, again, becomes the sine of alpha minus alpha, which is the sine of 0, which is going to be 0, or you go the other way and you get the sine of alpha times the cosine of alpha, and no, minus. See, I did it again. Minus cosine of alpha, sine of alpha. Well, again, these are the same thing. It's just commutative property. So flip around one of them, and now it's the same as the other. So yeah, we get 0. yeah, porque no los dos. And then the useful thing, right, this is not terribly useful. But still verifies the formula. All right, then the actual useful part is if we have alpha equals beta and we do the cosine of alpha plus alpha, right? Cosine of 2 alpha is going to be equal to cosine alpha times cosine alpha, and now minus sine of alpha times the sine of alpha. It's the cosine squared of alpha minus the sine squared of alpha, which is not the Pythagorean identity. Right, so this is our double angle formula. And then I keep saying to my students, all right, pretend you don't like cosines for a minute. How do you get this only in terms of sines? Okay, this is going to be 1 minus sine squared alpha minus sine squared alpha. So this is all equal to here 1 minus 2 sine squared alpha is cosine of 2 alpha. Or, interesting, or if you didn't like sines, you go back up to the top and you say, okay, this is the cosine squared of alpha minus parentheses 1 minus cosine squared of alpha. This is equal to the cosine squared of alpha minus 1 plus cosine squared of alpha, which is then 2 cosine squared alpha minus 1 is the cosine of 2, nope, not x, 2 alpha. Oh, now you do a rectangle. So all 3 of these are the same formula. And I keep telling my students, don't memorize these, okay? Know this one, know that one, and know how to get the other 2. Because this is all the brain power you need, is to remember this formula here. Right? Don't bother with all the rest of them if you could just remember that one, and remember that you need to use the Pythagorean identities to get the other 2. And besides, if you actually use it enough, you won't have to memorize it. It just comes naturally. And then the other thing I say is, okay, and the half angle identities, which are the next thing, are such a pain in the rear to try to remember what's what. Again, don't waste the brain space. Take these 2. And you say, okay, I've got cosine of 2 alpha is 1 minus 2 sine squared of alpha. So solve for the other one. So this is going to be the cosine of 2 alpha minus 1 is equal to negative 2. And you know what? That's even, I don't even do that. I swap which functions are where. So take your negative 2 sine squared of alpha and add it to the other side. Take your cosine of 2 alpha and subtract it to the other side. So this is 2 sine squared alpha is equal to 1 minus cosine of 2 alpha. Divide by 2, divide by 2. Sine squared alpha is equal to 1 minus cosine of 2 alpha all over 2. And now sine of alpha, absolute value of the sine of alpha, is equal to the square root of 1 minus cosine of 2 alpha over 2. Since you've got absolute values, you can put plus minus on the other side if you really feel like it. And it depends on what quadrant you're in. And then the only thing that the book does from here, really they do it at the beginning, but I wait until I'm here, is let 2 alpha be theta. So alpha equals theta over 2. Then this is the sine of theta over 2 equals plus or minus square root of 1 minus cosine theta all over 2. All right, and then do the other one. You got this one, do the same thing. So cosine of 2 alpha is equal to 2 cosine squared alpha minus 1. Okay, solve for the cosine of alpha that's there. So add 1 to both sides. 1 plus cosine of 2 alpha equals 2 cosine squared alpha. Okay, divide by 2. 1 plus cosine of 2 alpha all over 2 is equal to the cosine squared of alpha. Take the square root of both sides, and again, absolute value of the cosine of alpha is going to be equal to the square root of 1 plus cosine of 2 alpha all over 2. And again, cosine of alpha is equal to plus or minus square root 1 plus cosine of 2 alpha all over 2. And then again, do this over here too. So the cosine of theta over 2 is going to be equal to plus or minus square root of 1 plus cosine of 2 alpha. Nope. Cosine theta. All over 2. And again, you want the power reduction formula? Okay, power reduction formula is right there. You want the half angle identity? Again, that's here. You want the double angle identity? That's this stuff up here. So it's all of them at once. I never got used to the whole power reduction formula. I just thought it was like, oh no, I can't do that. It's terrible. Why would I ever? No. It's actually super easy. You just got to remember which one's which. So start at your double angle identity and then start working your way down. Alright, so yeah, power reduction formulas. We got double angle. Double angle identity. Again, here, and here, and here. All of them. Alright, and then unfortunately we got the one that's not nearly as useful or ubiquitous or anything else, which is when you do sine of alpha plus alpha. You end up with the sine of 2 alpha, which is sine alpha cosine alpha plus cosine alpha sine alpha, which again, we can just commute these two things, trade them around, and then we end up with 2 sine alpha cosine alpha. And that's it. There's no other hidden formulas here. That's just it. All right. Well, productive night so far. Oh, come on now. Nice. Just my OCD, don't worry. All right. So next question, do we have anything else? All right, if not, I'm going to switch over here to the book we have. Yep. Start looking at our series tests that I'm going to start doing more of them tomorrow for my Calc 2 class. So if there's anybody else here who is new tonight, welcome. I am Obi-Wan Pez. This is N-Simplex Pachinko. I am a variety streamer as well as a math and gaming streamer. So generally speaking, we will do math on Wednesday nights and variety streaming on Friday nights, where I do mostly gaming. I have on occasion done something like, let's see, we once did origami, where I folded some paper cranes. Have one here. Come on. There we go. There's the paper crane I folded on stream. I think I did this one anyway on stream. It could just be lying on my desk for no reason at all. But yeah, I was able to construct one out of, what is that, like 1.5 inch square? Maybe 2 inches square. And get a little tiny one. Fits in the palm of my hand or on a fingertip. Let's see. All right. So when talking about the value of a particular sequence, so for this, what we have is a particular function, which we're going to call f of x, which is then going to be a curve and totally not linear. Damn. Which is a continuous function. So that's condition 1. Condition 2 is that I believe f has to approach 0. Nope. Okay. I mean, that's one of the knock-on effects, but that's not actually what it says here. So f is decreasing. And f at n is equal to a sub n, our series value, for all n greater than or equal to some n value, which we call capital N, somewhere along the way. If those conditions are met, then the integral, which starts at n and goes to infinity, of f of x dx, the continuous function, must also either converge or diverge Right, must both either converge or diverge. Oh, Bertram, I'm sorry. Any particular reason that spring break is particularly sucky? We had ours last week. Hence why I was out. Yeah, I mean, I thought about streaming from the hotel room. No. It wasn't until like 8:45 I was like, huh, probably should put out a tweet that I'm not going to be here. Oops. Hope nobody showed up for any significant length of time here. Less work, yeah, okay. Hmm. Do you work at the institution where you're taking spring break from? Oh, okay. So how'd you get scheduled less on spring break? I managed to do that once, but... Oh, okay. Yeah, always possible. Oh well. So my explanation that I pulled for this one. Hmm. Well, that's crazy. The only time that I got really screwed over was when I had mono. I was like, oh yeah, let's... Actually, this was before the mono thing, but I was like, oh yeah, we can schedule me in for like, you know, all the hours. Only I didn't call them like... Really? Ugh, again. I didn't call them far enough in advance. They were like, yeah, we don't have room for you. I was like, fine. Man. What? Why do you do this to me? Alright, fine. Undo. There you go. Why? No. What is going on here? Trying to figure out how to... Alright, screw you people. That's it. I swear I could have moved these like 10 minutes ago. Works fine this time. Cool. Whatever. I undid. I just clicked undo till it disappeared. Right. So anyway. So my explanation for this was that here we choose some arbitrary n that's going to work and say, okay, either it's going to converge or diverge. So yeah, all right, that works. Fine. Fine, fine, fine. It doesn't really matter. I just started picking like from 1 on up to infinity because that just makes it easier. But it doesn't have to be. It can be that our function only works for some value above capital N, whatever that might be. But the main point here is really that if you're looking at a particular function whose sum is going to converge over time, then in this picture what we have is a f of x function whose sum, as determined by the integral, then the sum of discrete values so the sum of the discrete values is always going to be smaller than the integral to that point. So, if we were looking at the summation of all these rectangles, etc., 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 we're going to notice that these are always going to end up being smaller than, yeah, it's going to, never mind. It's going to always be smaller than the actual integral that's showing up here. Because as we can see with this particular integral, we've always got these little pieces that are stuck in there. So our summation values are always going to be smaller than the integral that's given there. And if the integral converges and also the summation is smaller, then it also must converge. There's no other possibility. How do you mean Pluto has yet to make a full orbit of the Sun? I'm curious of your metric. Is it because it's precessing? Because then that's not true. Like in our lifetimes, certainly not. But it's Orbital period's only like 200 years or something. Yeah, 248 years. Oh, okay. That's fair. Yep, discovered in 1930. So yeah, it's only been 90 years. $248. Over 248. So somewhere around 36.3% of its orbit. Since discovery. I mean, technically it's been 92 years, so I can change a little bit. 37.1. There's also no. Play this game again, are we? How does that? I really don't understand how this works. I mean, clearly. Close enough. I'm going to plop it down there and I'm not going to move it. Alright, so then we're looking at this in terms of, instead of drawing it in here, we could also draw our function here. This one is essentially f at x plus 1. So we shift everything back to the left one. And then if we say here, if the integral of f of x plus 1 diverges, and summation I goes from 1 to infinity of a sub I. You know what? That's not even, I don't want to go there. Just a sub I. And a sub I is always greater than or equal to f at f a sub n greater than or equal to f sub n then the summation of I goes from 1 to infinity of a sub I will diverge. Again, reason because here the integral is going to be, again, all these values here. And then we're going to have all of these extra bits that our series has, which our function does not. And if f at x plus 1 diverges, then so is this function. But here's the other thing. F at x plus 1, if we're trying to do the integral of f at x plus 1 dx from n to infinity, this is basically going to be the same. So it's not the exact same value, but it has the same behavior as integral from capital N to infinity of just f of x dx. And I suppose those n's might be slightly different numbers, again, plus 1, minus 1, that sort of thing. But the point is that, again, both of these things will diverge, or both of these things will converge. What's up? Go for it. Friends. Just gonna guess. Yep. Doesn't surprise me at all. Cash in on that 90s nostalgia from my generation. Mostly Xers, I'm guessing, but... Nope. I mean, they already did their work. So, realistically, right, if you create something and you put it out there into the world, you can still get paid on it. I know a friend who was doing some work for a company. I don't remember exactly what it was, but it was like web development type stuff. And that's the sort of thing that happened to him. He was like, all right, so I've got this app and I gave it to you, and what do you want me to do? And they're like, oh, just like wait until it breaks. And he's like, you want anything else? Do you want me to do something, do a different project? They're like, no, that's fine. You've got your salary or whatever. So he was just like, they didn't want to like overload him with work just in case it did break. And here's the thing is that app was making that particular company a lot more money than he was earning. So they gave him like, however much money it was. I'm going to guess probably around 100,000 a year to just, you know, come to the office and wait for it to break. It never did. So he was coming to the office and just hanging out like pretty much all day. And so at some point he was like, okay, I'm going to go crazy. So what I'm going to do instead is make a puzzle hunt. And that was the one I tried to pull up last week. No, week before. So it was before break. I tried pulling his puzzle hunt up, but unfortunately the website's down. I think probably I was the only person accessing it, and he just got fed up. So here with the remainder theorem. Yep. 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 So again, how much value added are we putting into the economy? Because you're not going to ever get paid as much as you are adding value to whatever company you're working for. So that also means that, again, I mean, you already posted it. They earn 2% of the show's syndication revenue. Where's that other 98% going, Bertram? Yep. Because I can tell you, it's not going to it's not going to the actors. I mean, clearly, it's certainly not going to the crew who showed up every single day, who are now on to other shows themselves. I know several people who are on crews or have been on crews, and yeah, basically as soon as they pack up, you're done. Oh yeah, it's all going to, you know, um, God, what was that was NBC, right? So it's going to NBC. Is that Viacom? I don't remember anymore. They're all. NBC. Oof. Okay, so Comcast and NBC Universal own NBC Corp. Hang on one sec. Let's see. So yeah, it's definitely going to uh, like the executives of those companies and their shareholders and other people like that. It's not. I don't even think it's going to the directors anymore, like the directors of the show. They might get a small cut, but it is a very small cut. Like I said, I guarantee that it's not going to like the people who ran the cameras or the people who, set up all the sound all the sound equipment every single day. Like they've been pushed onto other shows and are working their butts off, just the same as what you were saying before. You know, these people are going to work for 20, 30 years their before their bodies give out, and they're not going to be able to do what they've always been doing. They're going to be half of them are going to be in a forced retirement at some point. The lucky ones will get jobs elsewhere, you know, moving up through management or something like that, and who knows, but it's such a small percentage. The rest of them are going to have to, you know, work retail. Yay. Oops. I'm really slowing down here. What is going on? Like, nothing is eating my processes. Is eating my resources. That's so weird. Okay. Anyway. So there's this cool remainder theorem, which basically says that wherever you draw a line, so like if we draw an N here, capital N, a remainder theorem says that the sum that we have up until that point, so that's going to be our red here, is represented by the partial sum S sub capital N. Or the capital Nth partial sum. So then if we want to figure out like how much the rest of the sequence is going to have in it, we can't necessarily know for particular sequences. We're not going to be able to find what the rest of the series is. So if we just happen to know what the first, 5 or 100 or a million terms are going to add up to, and then either we're going to lose. There are a few different options. So maybe we've lost like precision. Goodness, dropping frames. What just happened? Hold up. Alright, there we go. Pig Louvre 101. Thank you for following. My name is Obi-Wan Pez. This is N-Simplex Vichenko. I am a math streamer who is currently doing Wednesday nights doing math and Friday nights doing variety games. So hope to see you around, and anytime you want to come in or just hang out and lurk, that's perfectly fine. So anyway, maybe we've lost precision, or maybe it's impossible to just do like a lot more partial sums. SDK! How you doing? It's the Phoenix Swarm. So, everybody, welcome SDK Phoenix. Shout out SDK. All right. Well, thank you so much, SDK. Ah, right. Yes, I did see you were doing Phasmo earlier. How'd it go? Skyfall, good evening. Yes, yes, I know. Get killed much? Slaughtered by ghosts. Good evening, Cedriel. How are we doing? Lots of spooks, yes. Sneaking up. Alright, so what we've got here is going to be... Am I super quiet? Or anything like that? I figure. Or is it just the base level? Goodness, Cedriel. Alright. Anyway. So what we've got is, may also because I've got a little bit of a chest cold at the moment, it's like bringing it down just a little bit. So, yeah. I tell this story frequently, but I love it so much. So I once had a really bad head cold, and like it just settled down into my chest and made my sinuses just really nasty. But it brought my voice down almost like half an octave, and it was, I mean, it's ridiculous. I've got a pretty deep voice to begin with when it's, you know, when I, at least, well, okay, I hear it as fairly deep considering. And then it was like much lower, and I'm just like, oh, this is pretty bad, but I kind of like it. And then I went to a choir practice. This was, you know, years before COVID. I went to a choir practice, and one of my friends is walking up, and she's wearing an N7 hoodie. And so I open the door for her and hold it for a minute, and then she walks up and she's just like, thanks. Like, you didn't have to hold it that long. And I just look at her and go, Shepherd. And she's like, oh my God. So, I mean, it was even lower than that. And that actually sounded sort of good to me in terms of like being close to Rex's voice. But it was that time where you've got that cold where it pulls your voice into that deep, rich area. And I was just like, yeah. All right, Connor, evening. Took Calc 2, thought series would never come up again. Yeah. So I only made the connection. I only made the connection to financial math, in particular. And this is pre-calc, but still, I only made the connection like last month that when you're doing the multi-payment option. So if you're making some sort of payment into a retirement account. Then what you're doing is you're saying, okay, I'm going to pay like $200 a month. And what's going to happen is that my first $200 is going to get interest paid on it to the tune of 1 plus r over n raised to the nt. And then my next month's payment is going to be 200 times 1 plus r over n raised to the nt minus 1 plus, and this goes on and on and on until you get to the point where you pay $200 and you get one interest payment of 1 plus r over n. And then this is a geometric sum. I was like, oh, idiot. Of course it is. So then when you flip it around, right, and you're adding an increasing geometric sum, this ends up being the total amount at the end is going to be your 200 times 1 minus, that's r to the n, which the amount that's being multiplied is parentheses 1 plus r over n, raised to the n is the exponent you have at the end, so that's nt, and then divided by 1 minus r, which is 1 plus r over n, which is the financial formula that we learned. The hell, man? No, seriously, what the hell? Okay, what just happened? Is that what's happening? Okay. It could be that my... Could be that Windows Update's trying to do its thing. Just stupid. I'm gonna yell at it. Hang on. Oops. No. System. Merry Moonface! How are you doing? Okay, that's not going at the moment, so maybe that's fine. What the hell is this? Go to details. Yep. Yeah, definitely. What service is this? You're not gonna tell me, are you? Cool. Get... What the hell? Yeah, so my CPU for some reason is using up a lot of its resources right now on something called, oh yeah, it says right there, Windows Update. But like it's not doing Windows Update right now. Like I just opened the thing. I just opened Windows Update to see if it was running, and it's saying it's not running. So maybe I just need to restart the computer soon. Very strange. Stupid thing. All right. It's got like 10 processes, which are all around 6%. Ah. You're not going to like that, are you? No, it's not going to like that very much. Alright, punk. Well, anyway, let's try that again. So, yeah, in the retirement process, you're saying if you pay off, like, if you're paying $200 a month into a particular retirement account, then the first payment you make is going to be $200 times the amount of interest you're going to get on that particular payment. So it's going to be 1 plus r over n to the nt. And then the next one, the next payment you make is 200 times 1 plus r over n to the nt minus 1, because it's going to make one fewer month's worth of retirement payments, or sorry, interest payments, whatever it's doing. So that goes all the way down until you get one payment that only has one interest period. So then when you take all this and you add them up together, the first term is going to be your 200. I guess technically this is plus a 200. Wow. Plus a 200 with no interest payment. So that's what's going to happen there. So we get this 200, which is our initial amount, right? The payment that we're making. And then times 1 minus r, the thing that we're multiplying by, which is 1 plus r over n to the nt, all over 1 minus r, which is 1 plus r over n. And then here, this is going to have 1 minus, those parentheses are superfluous at the moment, so 1 minus 1 is just r over n in the denominator. I guess technically it's a negative. But then we can flip this around up top and swap which one's negative and which one's positive. So, hey, that's behind my head. Okay. Damn. Did it again. So a equals 200 times 1 minus parentheses 1 plus r over n raised to the nt all over 1 minus 1 minus r over n. That's gone. And then again here, we can make this positive if we flip the sign up top. So make that negative, make that positive. So the formula that my students have to memorize in this particular financial math class, or mathematical literacy is the name of that particular class, is this nested 1 plus r over n to the nt minus 1 all over r over n. So they absolutely hate this. And they go crazy about this stuff and just like, oh, what formula do I need to use? What am I doing? I'm like, man, if you knew the connection in the back, which again, I only just figured out, then it would make it so much easier. But at the same time, they don't know sums, like series and sequences. So they don't know this. That's not going to work for them. Again with the thing. Auto ellipse. Anyway. So yeah, when we do this, it ends up being that they can, like, you know, find the form. Well, we give them the formulas because this is a fairly rudimentary class, but so many of them just did not know which formula to use where, and it's just like we talked about it in class at length. Oh well. All right. So, one last thing here. The remainder theorem, which is saying, like, if we know a partial sum up to a certain number of terms, so it goes out to this term, or this number n, and we've done a sequence, or we've added up all the terms in this series up until n, but maybe it's a lot of work. Maybe we just don't want to go many more terms than that, because whatever, it's fine. We can say here, if we take the integral of f of x dx starting from n and going to infinity, we just talked about that, yeah, just like an hour ago. We talked about the fact that there's these like leftover bits above the above the rectangles, which are going to form this small but non-zero remainder. So our integral here from n to infinity of f of x dx is going to be too big for the actual sum of the terms. So s sub n plus the integral from n to infinity of f of x dx is going to be greater than, and I'm writing this backwards, it's going to be greater than the sum going from I, goes from 1 to infinity, of a sub I. And that, in turn, is going to be greater than s sub n plus another integral of f of x dx, which starts at n plus 1. So if we go over here and we draw this line here at n plus 1, again, we're going to have all these red rectangles that we're trying to add up in terms of the sequence. But as we go further out, these green pieces will never fill the skipped rectangle, which do in violet. So the integral that goes from n plus 1, where is it? There. That goes from n plus 1 to infinity is going to have that extra amount above all of its rectangles in green, but those green pieces are never going to be able to make up the difference that is in this purple rectangle. So it's never going to make it. It's always going to be less than the true sum here, which then is going to be less than the integral starting from n. So when you look at this, we can actually start doing like numerical analyses on the computer and saying, well, look, I'm just going to let the computer find this stuff and be like, how much are we missing out on? How close is our approximation to the true value of the sequence? Now, we may not know, or series, sorry. What is the true value of the infinite series might be an impossible question. It's perfectly possible to have an impossible answer, that we can't find it. But that'll allow us to say, okay, this partial sum that we figured out to this point, how far off is that? So if we can find the integral at that point off to infinity, and also one ahead to infinity, that gives us an upper and a lower bound. So then we can say it's between these two values. And if they're sufficiently close to each other, we can be like, it's close enough. So we did that in my last class with my Calc 2 students. It's interesting and challenging. And let's see. Yeah, there we go. Strange. All right. So I think that's probably good for the night. If anybody does have any other questions, let me know, because like I could do more calculus stuff, but you know. Let's see. All right. So tonight we are going to train this raid over to Jason Charles Miller, who is oops, Connor. Yeah. So most of the time I'll do a fairly in-depth explanation of whatever it is that I'm trying to do. Here. So earlier we had looked at proving the sum and difference identity for angles. So this is something that I did in pre-calc today. Um, I've got time for it. It's okay. We could have done a bunch of like examples and things like that, but at the same time, I feel like having them try out, getting from point A to point B, and the way that I do it is kind of a Socratic style. So I'll just keep asking questions and get them to lead me through the whole process. And most of the students get it. And then they'll be like, okay, I need to practice this. And they can go home and practice it on their own. Now, this is a fairly traditional lecture style, slightly made different because of the Socratic stuff that I do. But it's still kind of dated a little bit. So, like, it's interactive and it's interesting to the ones who are engaged. To the ones who are not engaged, this is ridiculous and stupid, and they're going to hate it. So. Yeah, well, the other thing, Megalomorph said he'd never actually seen this before, was if we, and to be fair, I hadn't either, if we start from the cosine sum and difference formula, you can get the sine sum and difference formula by using the cofunction identity, and then associating, no, not that way, associating which two things you bring together. Right. And the thing that I'm trying to really like get them to focus on is the fact that like starting with pre-calc to a small extent, but my Calc 2 class to a much larger extent, and to my differential equations class almost entirely, these classes are no longer about getting results. The classes themselves are not about getting a result. So like, you must learn this one thing. You must learn this thing because it's going to definitely be applied in your life. Like, no. A lot of things are not going to be applied in your life. However, what is important is to build your toolbox. To say, like, I can do this thing should I need it. Because the day will come when you're like, I need an impact wrench, and you don't have one. So the day will come when you happen to need this trigonometry thing, and you're like, I don't remember how to do this, or I never learned it, or whatever. And the question is that student, is that former student, going to ever realize even that that's the thing they need? So, like, if they know that this thing is the thing they need, they might be able to go back and look it up and figure it out. If they have no clue at all whatsoever what they need, they're just going to get frustrated and hire somebody like me. And I'll do it, but I'm going to charge through the nose if I'm not interested in the particular thing, or if it's hard, or if I'm going to need to do some research. So, I will charge market value for whatever work I am being asked to do. Sure, I'll do it, but yeah, it could be $100 an hour or more. This is one of the things that I told a couple of my students, like, in the past few years. I was like, yeah, I will do this sort of work, but if I'm not particularly, like, invested in getting it done, I'll charge more than market value because I don't really want to do it. But, you know, you want to hire me? All right. Professional mathematician, 150 bucks an hour? Let's do it. That being said, right? Mizahide, how you doing? That being said, like, if I don't know how to do something, if it's not my area of expertise, I'm not going to charge more. That's certainly not what I'm going to be doing. I will charge more than market value if I am an expert in the field and I don't really feel like doing it. I'm not 100% invested in this particular project. So yeah, we derived the sine sum and difference formula today in class, and a couple of the students were like, "Wow, that's crazy! Never seen that before." Speaking of stonks, got this one here just for you. The amount in a retirement account given a certain payment and all the other parameters that are usually around in compound interest. So this is a repeated payment formula, which happens to use the geometric sum formula to figure it all out. Anyway, so I think the only, like, I don't have time for passion topics, which is unfortunate, but most of the stuff that I will spend time on that I don't really have time to explain is going to be like some of the historical perspectives of math. Because like we just don't have time for it really. I will spend time discussing the Newton-Leibniz fight. I will I will spend time discussing some of the basics of all of the, like, major players in how a certain topic came about. If I've looked it up, obviously. I'm not going to make up any stories on the spot. That'd be awful. But, like, I went into, when we were talking about polynomials in pre-calc, I went into the Galois theory that there are no there are no general solutions for polynomials of fifth degree or higher. Yeah, well, the one that I had was only for math teachers. So, like, you could take it as an elective, but there were so few people who were going to do that just because they're, pure math majors had such a busy course load anyway. And this was a junior level class, so it wasn't really like at the level where you need to take electives. Like, the elective level was senior level / master's 1. Fifth degree, yeah. I mean, that's true, but we're so the context that we're having here is all of the I have absolutely no idea what the bring radical is. Okay, well I'm gonna have to look that one up. Ultra radical of a real number. Unique. Oh, interesting. Unique real root of the polynomial x to the fifth plus x plus a. Okay, so that's why we also don't talk about it, is that we do all of the stuff that I do is one-to-one. So, or, well, I shouldn't say everything we do. Everything we do is going to be a function, and then, therefore, the bring radical is not a function because it is multi-valued. So, yeah. I mean, apart from the fact that I've never heard of the thing. So okay. But yeah, anyway. The elective level at the University of New Hampshire for math majors was again our senior level / masters 1, which allowed you to take like any 4 of the following 10 classes or something like that. So my spouse and I both needed to take the linear algebra class that was at that level. She needed to take several others, but she was also given the choice of, like, you could do stochastic processes, you could do statistics, like calculus-based statistics, you could do a bunch of other stuff. She chose topology, complex analysis, real analysis, several others. I can't remember exactly what it was, but but yeah, she ended up taking a really good, like, solid course load, and I didn't have that opportunity. My 700 level classes at the University of New Hampshire, because I was a math education major, were the philosophy and psychology of education, which I loved both the classes, don't get me wrong, but there was a lot of reading, and I just did not want to read them. It was so awful. I shouldn't have been like that. But I read most of the books. Psychology and philosophy of education. A teaching math 7 through 12 class, which was all about, like, methods. And I really like that. I never, in my entire course load, I never learned how to write a lesson plan. Like, not really. We did some basic stuff, but we didn't ever, it was never like an assignment to write a lesson plan. We had to, like, write some basic curriculum notes, but it was never a lesson plan properly. Oh, and my senior seminar, which was get up in front of the class and now teach. Go. So that was fun. But those were like my 700 level classes. And then linear algebra. And there must have been another one. And I can't remember what it is now. Maybe, oh, you know what? It might have been just the Teach 7 through 12 class, because that was a math class, not an education class. So I think I only had one per semester of the 700 level stuff. And then education was another 1 to 2 classes each of those. So that was fun. But it wasn't really until my master's where I took a lot of those upper level stuff. So I ended up doing the differential equations route, and had a basic differential equations class, and then the partial and nonlinear differential equations classes, which were amazing and I loved them. But I'm also really glad that I took neural networks before taking them, or maybe concurrently, but either way, my neural networks class gave me a lot of a boost in PDE. I think those were concurrent, so it gave me a big boost in PDE, and then it gave me a huge boost in nonlinear because I was able to create a self-organizing Kohonen map and make a predator-prey, predator-prey scavenger model, which then was a self-organizing map. I showed that on stream once. It was a little weird, and I tried to make it. It reached equilibrium too quickly if I didn't do something weird with it and like put splotches basically inside the map somewhere. Anyway. So yeah, my passion stuff is usually my passion projects are usually historical related. I was supposed to this semester work on one that was like going back and really looking into like the history of math, particularly related to Black History Month, and I ended up like having 20 other things on my plate, and I was like, oh, this sucks. Why didn't I actually spend the time doing that? So I'm gonna do that for next year, and hopefully I'll be able to like present it here or something. Strip my name out of it so I don't get doxxed again. Don't dox myself again. Yeah, and we also did a combinatorics class, which had the same sort of like stochastic processes, Hamiltonian paths, and using matrices to do all sorts of crazy stuff. Okay, all right, let's get out of here. It's 1:45. Oh, you know what? Jason's probably not even on anymore. He is. Okay, he may not be on for very much longer. I know he usually wipes his voice. So let's let's go see Jason Charles Miller for however long he might be in. Of course, it's not going to tell me. So anyway, hope you all have a good week. I am going to be back on Friday for gaming. This week we're probably doing some more Valheim to do some base building and find out where the next like big enemy is. I've got to go into the woods to find. I'm singing. Got to go into the woods to find the next marker to figure out where the thing is, and hopefully not get killed by too many trolls. So we'll see how it goes. And next Wednesday we'll be back for more math stuff. Feel free to drop any questions into my email, which is just thechannelname@gmail.com. I will occasionally check that. I have been really bad about email lately. So apologies if anybody has actually sent me anything. But we will see you hopefully this Friday. Everybody's welcome to come and lurk, or just, stop in, say hi, and then head off somewhere else. Or come in next Wednesday, and we'll see you for more math stuff. So have a good evening. This is Obi-Wan Pez for N Simplex Pachinko. Have a good night.